3.9 Lesson 2, Exponential and Logarithmic Functions. Our objectives for today's lesson are: 1. You will know a new differentiation rule. The derivative of the exponential function with base b is natural log of the base times b to the x. And you will know how this differentiation rule is derived from the one that we learned yesterday for the exponential function e to the x. And we will be able to find derivatives of exponential and logarithmic functions. So yesterday we looked at the function y is equal to e to the x. That's called the natural exponential function with the natural base e. Today we're going to be looking at exponential functions with base b. So for example, you could have y is equal to 2 to the x, or y is equal to 8 to the x. So a base other than e. And the natural log function, we looked at that yesterday. Later we'll be learning about logarithmic functions with other bases. Yesterday we learned about these three properties of logarithms that we were able to use to rewrite our function before differentiating. That's called expanding the logarithm using these properties of logarithms before differentiating. Yesterday we learned this differentiation rule for the natural exponential function. The derivative of the natural exponential function y is equal to e to the x is itself. Today we're going to see that for an exponential function with base b, the derivative of an exponential function with base b would be natural log of the base times b to the x. And we'll see how we can derive this exponentiation rule from the we will see how we can derive this differentiation rule from the derivative of the natural exponential function that we learned yesterday. But let's demonstrate what this rule is saying. It's very easy. For example, if you have the exponential function with base 2 and you want to find the derivative of it, it is simply natural log of the base times the function. So if you have y is equal to 5 to the x, the derivative would simply be natural log of the base times the function. So if you have y is equal to 10 to the x, the derivative would simply be natural log of the base times the function. So that's the new differentiation rule that we're learning today. And we'd like to go ahead and see how we can derive it from the differentiation rule for the natural exponential function. So to derive our differentiation rule that we're learning today from what we learned yesterday, we need to begin with our function with base b. So I write y is equal to b to the x. But we have to somehow rewrite our function that we have in terms of the base e, so we can use the differentiation rule that we learned yesterday. And here's how we can accomplish that. We can write y is equal to e to the natural log of b to the x power. Now what is e to the natural log of b? It's actually equal to b. And the reason is the natural exponential function y is equal to e to the x and the natural logarithmic function ln of x, they're inverse functions. And what you have here is a composition of two inverse functions. So they'll undo each other and the final output will be the same as the original input. You can also understand why this must be true, thinking in terms of the definition of the logarithm. If you look here, this means the power to which the base e must be raised to get b. And if you raise e to that power to which it must be raised to get b, you will get b. Remember, a logarithm is an exponent, so here you're raising e to the power to which e must be raised to get b, so you'll get b. So now you understand that the base b can be rewritten as we've done here. And the purpose for doing that is now our function has been rewritten so that we have the base e. So now we're one step closer to being able to use what we already know to come up with our new differentiation rule. So now we will continue rewriting our function. Notice that here you have the power of a power. So for example, if you have a squared to the third, you can multiply the exponents and get a to the sixth. So we're going to do that with what we have here. We can multiply our exponents and we will get e to the natural log of b times x. Now we can use what we learned yesterday to find the derivative of this function, because we have now a composition of two functions where the inside function is natural log of b times x and the outside function is the natural exponential function. So what you have is y is equal to f of g of x, y is equal to f of g of x, where g of x is natural log of b times x, and f of x is the natural exponential function e to the x. So we have e to the natural log of b times x. So what you have is a composition of two functions here. So you can find the derivative by using the chain rule. So now to use the chain rule, we will begin by finding the derivative of the outside function, which is the natural exponential function, evaluated at the inside function. And then we have to multiply by the derivative with respect to x of the inside function. This is what the chain rule says we should do to find the derivative of a composition of two functions. So again, here's the chain rule. Take the derivative of the outside function, evaluate it at the inside function, and multiply by the derivative of the inside function. So now we'll go ahead and complete our derivation. So what is the derivative of our inside function? You'll notice that you have a constant multiple of the identity function. The derivative of the identity function is 1, so the derivative of natural log of b times the identity function will be natural log of b times 1. So this derivative is just 1. It's just natural log of b. Just like if you had the derivative with respect to x of 7x, that would be equal to 7. So here, the derivative of natural log of b times x is equal to natural log of b. So I write the derivative of the inside function, natural log of b, and then I have e to the natural log of b times x. And now I'd like to go ahead and use properties of exponents to rewrite what I have here so that it would be b to the x. So we have y prime is equal to natural log of b. So you can write what we have here using properties of exponents as the e to the natural log of b to the x. You have the power of a power, so when you multiply the exponents, you'll have e to the natural log of b times x. And what is e to the natural log of b? As we had discussed earlier, that would just be b. So we have b to the x. So y prime is equal to natural log of b times b to the x. So this is how we derive the differentiation rule for an exponential function with base b. And you can see in our derivation that we're using the differentiation rule for the natural exponential function that we learned yesterday. So we know today that the derivative of b to the x is natural log of the base times b to the x, and we just looked at where this rule comes from, how we derive it from the differentiation rule for the natural exponential function. Now we will look at objective 3. You'll be able to find derivatives of exponential and logarithmic functions. Here's our first example. We want to find the derivative of the function y is equal to cosine of 4x. So before we start, let's look at the function. And we should see that we have a composition of two functions. The inside function is 4 to the x, and the outside function is cosine. So because we have a composition of two functions, we know we will need to use the chain rule. In addition to the chain rule, we know we have an exponential function with base b, so we will have to use what we learned today. The derivative with respect to x of the exponential function with base b is equal to natural log of the base times the exponential function. Furthermore, we also have the cosine function, so we will also have to remember that the derivative with respect to x of cosine of x is negative sine x. With this, we're ready to find the derivative of the function y is equal to cosine of 4 to the x. The inside function, or the first function, is 4 to the x, and the outside function, or the second function, is cosine of x. So using the chain rule, we begin by taking the derivative of the outside function, evaluate it at the inside function, and then we multiply by the derivative of the inside function. So we have y prime is equal to the derivative of the outside function cosine is negative sine, so we have negative sine, evaluated at the inside function of 4x, and then we multiply by the derivative with respect to x of the inside function 4 to the x. And what is the derivative of the inside function 4 to the x? We're going to use our differentiation rule that we learned today, and we write y prime is equal to, so we have this factor of negative 1, and then we know that for this derivative we're going to have natural log of the base times the exponential function. So putting that together, you're going to have negative 1 times the natural log of the base 4 times the exponential function 4 to the x, and then you will also have sine of 4 to the x. So that is the derivative for number 1. Number 2, we want to find the derivative of the function y is equal to 4 times the natural log of sine of x cubed. So when you look at this function, first of all, you'll see that you have a constant multiple multiplying a derivative. So we remember one of our differentiation rules. If you have a function that's a constant multiple of a differentiable function, the derivative of your function will be the constant times the derivative of the differentiable function. So in what we have to do is we just find the derivative of natural log of sine of x cubed and multiply that by 4. Now when you look at natural log of sine of x cubed, you can see that you have a composition of 3 functions. So you'll have to use the chain rule here to find the derivative of natural log of x cubed, and you'll have to use the chain rule twice. So let's see what functions we have in our composition of 3 functions. So you can write y is equal to 4 times f of g of h of x, which you can write as f of g of h of x. And what is the insidemost function in our composition of three functions? You can start with the variable x, and the first thing that's being done to that is it is being cubed. So the insidemost function, the first function in our composition of three functions, is x cubed. The middle function in our composition of three functions is what we're doing second. We're taking sine of x cubed, so the function g, the middle function, is the sine function. And the outside function is what we're doing third. We're taking natural log, so we have natural log of sine of x cubed. Our three functions are, the insidemost function is h of x, the middle function is g of x, and the outsidemost function is f of x. So now that we have these three functions, we know we will have to know the appropriate differentiation rules. So we will have to use the power rule for the insidemost function, and I will write the other two differentiation rules for the middle and the outside functions. The derivative of sine x is cosine x, so we can write the derivative of sine x is cosine x. And the derivative of the natural log function is what we learned yesterday. It is 1 over x. So with this, we're ready to find the derivative of our function for number 2. So we're going to write y prime is equal to the constant multiple 4 times the derivative of natural log of sine of x cubed. And for the derivative of natural log of sine of x cubed, we have a composition of three functions, so we must use the chain rule. So we begin by taking the derivative of the outside function, evaluate it at the inside function. This is using the chain rule. So how do you find the derivative of natural log? It is 1 over the argument. So whatever the argument is, you'll have 1 over that. So you have 4 times 1 over sine of x cubed. And then, following with the chain rule, multiply by the derivative with respect to x of the inside function. So we have the derivative with respect to x of the inside function sine of x cubed. Now, sine of x cubed is also a composition of two functions. So to find the derivative of sine of x cubed, you'll have to use the chain rule again. So we have y prime is equal to 4 times 1 over sine of x cubed, which I can write this way. And then the derivative with respect to x of sine of x cubed, the derivative of the outside function, which is sine, is cosine, and we have to evaluate that at the inside function. So we have cosine of x cubed, and then multiply that by the derivative with respect to x of the inside function x cubed, which we can use the power rule to find that the derivative of x cubed is 3x squared. So we have y prime is equal to 4 times 3x squared, 3x squared is coming from here, times cosine of x cubed over sine of x cubed. And of course, 4 times 3 is 12, so I can write 12x squared. And if I wanted to, I can do something here as well. You can notice that we have cosine of x cubed over sine of x cubed. The arguments of these two functions are the same, and cosine over sine is cotangent. So I could write cotangent of x cubed here, and that would be my answer for number 2. 12x squared times cotangent of x cubed. Number 3, find the second derivative of y with respect to x for y is equal to natural log of x cubed. So to find the second derivative, we will find the first derivative and then find the derivative of the first derivative. So when you look at our function, you should see that we have a composition of two functions. The inside function is x cubed and the outside function is natural log. So how do we find the first derivative of this composition of two functions? One option that you have is to use the chain rule. There is another option that would allow you to avoid the chain rule for this particular problem. You can use a property of logarithms to rewrite the function. So you have y is equal to natural log of x cubed, and the property that we want to use is called the logarithm of a power. So using this property of logarithms, called the logarithm of a power, I can take the 3 here and bring that to the front. So now we have y is equal to 3 times the natural log of x. So now we can find the first derivative, y prime. You can also write dy dx. It will be equal to, here we have a constant multiple times natural log, and the derivative of a function that's a constant multiple times a differentiable function is the constant multiple times the derivative of the differentiable function. So we will have 3 times the derivative of natural log of x, which is of course 1 over x. So 3 times 1 over x, which you can write as 3 over 1 times 1 over x. Multiply the numerators and the denominators, and you get 3 over x. To find the second derivative, we must now find the derivative of 3 over x. So how do we do this? You have to rewrite the function using properties of exponents. If you have 3 over x, that's 3 over x to the first. You have a power in the denominator. You can take it to the numerator, and when you take it to the numerator, the exponent will become negative. So this is equal to 3 times x to the negative 1. So you will have 3 times x to the negative 1. So we rewrote 3 over x using properties of exponents. We took x to the first from the denominator to the numerator, and now we have x to the negative 1 power in the numerator. This is the correct way of doing the problem, and now you will find the derivative, the second derivative of y with respect to x, by using, once again, the differentiation rule for finding the derivative of a constant times a function. Our constant is still 3. Our function is now a power function, so you have to use the power rule. So you have 3 times. Using the power rule, we have negative 1, bring the exponent to the front, x to the, reduce the exponent, subtract 1 from the exponent. Negative 1 minus 1 is negative 2. So you can write that as negative 3 x to the negative 2 power. And of course, you can rewrite x to the negative 2 as a power with a positive exponent by taking the power from the numerator to the denominator. So our final answer is negative 3 over x squared. And what is this? This is the second derivative of the function y is equal to natural log of x cubed. In this example, we have f prime, and we want to find an antiderivative function f of x. So to find an antiderivative is the same as saying finding an indefinite integral. So we can find f of x by taking the indefinite integral of f prime of x. This means we're finding what we call an antiderivative, or a function whose derivative will be f prime of x. So f prime of x is 6 times e to the 3x. So now we have to think backwards. So we know that the derivative of the natural exponential function is itself. So an antiderivative of the natural exponential function would also be itself. The only issue is we have a composition of functions here where the inside function is 3x. So we should definitely have the constant multiple 6. We should have e to the 3x. But if this is it, and you should have something called a constant of integration as well, if this is it, it wouldn't be quite correct. And the reason why it would not be quite correct is if you try taking the derivative of what we have here, you will have 6 times the derivative of e to the 3x. You would use the chain rule. You would have e to the 3x. Multiply that by the derivative of the inside function 3x, which is 3, plus the derivative of a constant, which would just be 0. So it's almost correct, but you would not have 6 times e to the 3x. You would have 18 times e to the 3x. We don't want 18 times e to the 3x. We want 6 times e to the 3x. So we have to compensate by dividing by 3. So we go back to the previous step, and we've got to make sure that here we're dividing by 3. So our final answer should be f of x is equal to 6 divided by 3 is 2 times e to the 3x plus some constant of integration. In other words, you can have any constant in place of c, whether that constant is 0, a positive number, or a negative number. You can verify that we found the correct antiderivative by taking the derivative of f of x, and it will give you 6 times e to the 3x. Today we learned a new differentiation rule. We see how to derive that from the differentiation rule for the natural exponential function, and we looked at some examples for finding derivatives of exponential and logarithmic functions.